Last class, we solved a few problems pertaining to basic, uh, pertaining to the first lecture, that was Introduction to Rings. This class will continue with homomorphisms. Let R and R prime be rings. A homomorphism is a function phi from R to R prime, or it can be from R prime to R. Um, since R and R prime are arbitrary rings, doesn't matter. We'll say phi is from R to R prime. Such that, do you remember group homomorphism? What was the condition for a group homomorphism? Yes. Yeah. So it should hold for both the addition and multiplication operation. Phi of A plus B must be equal to phi of A plus phi of B for all A, B in R. Phi of A into B must be equal to phi of A into phi of B. Where on the LHS A into B is the into operation in the ring R. But on the RHS, phi of A into phi of B is the into operation in the ring R prime. But there is one additional condition when it comes to rings. And this condition is that phi of 1R is equal to 1R prime. 1 is the multiplicative identity. Instead of E, we will use 1 a lot of the time when it is multiplication. And when it is addition, we will use 0. So when we say 0, it doesn't necessarily mean the zero number, integer 0. For example, the 0 of the matrix group under addition is the 0 matrix. So when we say 0, we actually mean the additive identity, and when we say 1, we actually mean the multiplicative identity. So it's not the integer one. And to differentiate between the 1 in R and R prime, we can use subscript. So we write phi of 1R is equal to 1R prime. So this condition was not there in groups. It was true in groups um, with respect to addition. So phi of 0 was 0 if you took the additive group. Uh, Phi of the identity, E was the identity. So if it was a multiplicative group, then if you took a homomorphism, then phi of 1R must be 1R prime. That was true in groups automatically, but we'll take that as an additional condition in rings. Yes. That is automatically there from the property that phi of A plus B is equal to phi of A plus phi of B. because phi of 0 plus 0 is phi of 0 plus phi of 0. But 0 plus 0 is 0 only, right? So phi of 0 on the left hand side, we take A is equal to B is equal to 0. Then in point number 1, phi of 0 plus 0 on the left hand side will become phi of 0. And on the right hand side, you'll have phi of A plus phi of B, which is phi of 0 plus phi of 0. Then you add the additive inverse of phi of 0 to both sides. And you get 0 is equal to phi of 0. So that you directly get from the um, from the operation preservation. That is phi of A plus B is equal to phi of A plus phi of B. That directly gives you that phi of 0 must be equal to 0. But if you take phi of A into B is equal to phi of A into phi of B, that does not directly give you that phi of 1 is equal to 1. Because if you take A is equal to B is equal to 1, you get phi of 1 on the LHS in the second point here. Um, but on this side, you'll get phi of 1 into phi of 1. But see here, we can't add we can't multiply by the multiplicative inverse of phi of 1 on both sides because phi of 1 might not have a multiplicative inverse. We are dealing with rings. So it is possible to have operation preservation without actually having phi of 1 is equal to 1. That's why we have to separately include this as a necessary condition or in the definition itself. Okay. For example, um, let us take both the rings to be the ring of integers. Now, what kind of homomorphism can we get? See, this phi of 1 goes to 1 that produces a lot of constraints on what the homomorphism can be. So, it is more restrictive than group homomorphism. If you remember the homomorphism lecture, it's lecture, what is it? Lecture 7. We had this example here, see, the homomorphism from Z to Z, where we said fix an integer n and phi of A is n times A. So depending on the choice of n, you would get different homomorphisms here, right? If n was 1, you get phi of A is equal to A, which is the identity map. If n was 2, you would get phi of A is equal to 2A, which is doubling. So 1 goes to 2, 2 goes to 4, etc. So on phi of A, for different values of n, you would get a different homomorphism. Is there any other? Okay. So you had multiple homomorphisms from the ring of integers to the ring of integers. But this condition, third condition, that phi of 1 must be equal to 1, places a lot of restriction. And it turns out that there is actually one ring of homomorphism from Z to Z. And we'll see why that is. We have, let phi be the homomorphisms from Z to Z. We need phi of 1 to be equal to 1. So now what happens? Earlier we had that in group homomorphism we had phi of A is equal to NA. We could pick any n and we would get a different thing. But this is not possible now, right? P of 1 should be equal to n into 1 is n, but this must be equal to 1 here. So n must be equal to 1. So P of A is equal to A. So at least when you look at homomorphisms of this type, there is only one. You're forced to choose n is equal to 1 because phi of 1 must be equal to 1. Even otherwise, phi of 1 is 1 means uh, so from the first property that phi of A plus B is equal to phi of A plus phi of B, we get phi of 0 is 0. Now phi of minus 1 plus 1 is phi of 0, but it's also equal to phi of minus 1 plus phi of 1. So 0 is equal to phi of minus 1 plus 1. So phi of minus 1 is minus 1. Now for any n greater than 0, phi of n is phi of 1 added n times. So this is equal to phi of 1 plus phi of 1 plus etc. plus phi of 1. There are n terms there. So this is simply equal to n into phi of 1. But phi of 1 is 1. So this is simply equal to n. Similarly, for n less than 0, phi of n is phi of minus 1 added to itself with n terms in the sum because n is a negative number, right? This is equal to phi of minus 1 sum of phi of minus 1 n terms. So that becomes n times minus 1, this minus n. So there is exactly one homomorphism from the set of integers, from the ring of integers to the ring of integers. And that is the identity homomorphism. Yes, that thing comes from groups itself. Now we saw from Z to Z. Next we see. Next I claim that there is only one ring homomorphism from Z to any ring R, and we will use the same logic. We have phi of 1 must be equal to 1 R, and phi of 0 must be equal to 0 R. That comes from first property. That comes from operation preservation under addition. Then phi of minus 1 plus 1 is phi of minus 1 plus phi of 1, but it's also equal to phi of 0. So 0 R is equal to phi of minus 1 plus 1 R. So phi of minus 1 is equal to minus 1 R. Now this completely determines again phi of n for any integer n is simply one are added modulus, that is magnitude of n times. There are magnitude of n terms in the sum. That's the only homomorphism. That is clear, right? Any doubt in that? Yeah. So from Z to any ring, you have only one homomorphism. I've written, right? P of n. So the domain is integers. P of an integer n. You take the identity in the ring R and add it modulus of n times if n is positive. Or you take is n terms if n is greater than 0. Or if n is a negative number, then you add minus 1, minus of the identity. We didn't know, we didn't study homomorphism for that. Otherwise, we could have simply defined only isomorphism. There was no need to go to homomorphisms. I can't give you applications for everything, right? That is dependent on the field. Somewhere someone would have used. I don't remember. Otherwise, see, simply if another possibility is it simply of mathematical interest. That is also there. Sometimes things are done just because they're interesting and not because they are used anyway. But the things that are fundamental like this usually have some applications, but they will be very niche and you'll have to go to that particular field and see. I don't remember any applications. Um, the homomorphism, no. Uh, it is used in coding theory, this homomorphism. The linear codes are actually homomorphisms from one field to uh, one vector space to another. They're from vector space to vector space, but still the idea of homomorphism is the same, right? Uh, Similar to here, how there's a slight change since there are two operations, plus and into. We had operation preserving in both addition and multiplication. Uh, Something like that will exist for vector spaces also. There is homomorphism of vector spaces between or homomorphism between two vector spaces. There, the message is a set of k bits, and that in a linear code, in any code, the k bits will be transformed into a code word of n bits, where n is greater than k, by adding some parity or redundancy to it. In terms of linear codes, that is done using a matrix multiplication. So there is you have a k length vector and you multiply it with a k by n matrix, then you will get an n length vector. This has some useful, and if the matrix is good, you will get some useful properties that are needed for error correction. So this multiplication, this linear transformation is a homomorphism. And in homomorphism, what happens is we didn't study it further because we went to rings, but in homomorphisms, the uh, kernel, there are some theorems that relate the kernel and the cosets of the kernel and the image. So um, you have the kernel, which is a subgroup. Then the cosets of the kernel form a partition of the domain, kernel and its cosets. Uh, and the partition is such that under the homomorphism phi, all the uh, all the elements in a coset will go to the same image. Okay, so it splits the domain into equal size sets where inside each set that element goes to the same, all the elements go to the same image. That is used in decoding of this code words called standard array decoding. So there it's not an isomorphism because the message is from smaller vector space, that is it's from let's say it's from f power k, that is k bit messages, but the code words are from fn, that is n bit code words, but not all n bit vectors are covered by this transformation. So if you have a binary message with k bits, let's say you have k is 2, 0, 0, 0, 1, 1, 0, and 1, 1. To each of them, you map a 4-bit message. Right? 0, 0, 0, 0, and let's say 0, 1, 1, 0, say 1, 0, 0, 1, and then 1, 1, 1, 1, something like that. These are 4-bit messages, but the vector space of 4 bits has 16 vectors, right? 2 power 4, 16 vectors here. Here there are only 2 square 4 vectors. So each of the 4 vectors in the domain, you are assigning only one vector in the codomain. But the codomain is actually larger than that. So it's not an onto function. So it's not an isomorphism. Then for decoding, you'll use the parity trick matrix, and this will all come in error correction. So you'll find the syndrome, and all the messages in the same coset give the same syndrome because it is a homomorphism. Okay, that you see now this explanation, I don't know how much you understood, but like that when you go to a particular application, there you will find these ideas useful. Yeah. You get a parity check matrix. Then for decoding, you get the syndrome by multiplying the parity check matrix with the received vector. and the syndrome of a set of vectors will be the same. So the set of all vectors, n-bit vectors, will be divided into sets of equal size, where each of those will give you the same syndrome. So you can only pick one of the things to be the coset leader. There will be cosets there. And based on the syndrome, you decode to the coset leader. Yeah, but each coset will have multiple vectors. So it could actually have been, yeah, something like that. Uh, there, the transformation, uh, the kernel is the set of all code words for the parity check matrix. The code words are the null space of the parity check matrix. When null space is from linear algebra, but actually it is the every linear transformation is a homomorphism. Uh, and the null space is actually the kernel of the homomorphism. And the kernel and its cosets will form a partition of the entire vector space, such that each coset goes through the same uh, syndrome when you multiply by the parity check matrix. So there you use homomorphism, the idea of homo. Of course, even without knowing homomorphism, you could solve it, but understanding through the perspective of homomorphism makes it clearer that the cosets of the code word and the cosets of the code word actually partition the entire vector space. That is more clearer from the perspective of homomorphism. Yeah. And we use isomorphism where um, if some operations or some mathematical steps are difficult in one of the forms. So both the rings are identical in their operations and how they behave. But for example, if there is an isomorphism between integers and matrices, of course, an isomorphism is not there like that. But if there was something like that, then instead of working with matrices, you could have worked with integers, and then final result you could have used the inverse transform to get back the matrix. Yeah. So in that case, the isomorphism is useful. Okay. Now we have seen that from integers to any ring, there is one particular homomorphism. That homomorphism maps the identity element in the integers, which is the element 1, to the identity element in the ring R. And then for any positive integer n, to get phi of n, you add the identity in R, 1R, n times. For any negative integer n, you add minus 1R minus n times, because minus n is, or the magnitude of n times. For example, consider R is Z mod 4Z, which is 0 bar, 1 bar, 2 bar, 3 bar. So if phi is a homomorphism from the set of integers to Z mod 4Z, then phi of 1 is 1 bar. Phi of 2 is phi of 1 plus phi of 1 plus 1, which is phi of 1 plus phi of 1, which is 1 bar plus 1 bar, This is 2 bar. Phi of 3 is similarly 3 bar. Phi of 4 is what? Yes, Phi of 4 is 0 bar. So for any n, we can show for negative numbers also. P of n will simply be equal to n bar. That's the only ring homomorphism from Z to Z mod nz. So this works for other rings also. I mean, Z mod for any Z mod nz. P of n is n bar. Okay, the n is being used twice here, so it might be confusing. We'll say phi of k, phi of an integer k is equal to k bar. Here k bar is, if you want, you can find the modulo of k mod n, and that will give you the equivalence class. Is this homomorphism understood? Yes. Yeah, it would still be k bar, but if you want the representative bit to be within to be less than 4, then you can take the modulo of 4 and you'll get a number less than 4. Next example is this is that's all for Z to R. We already having we already have uh, we have already completely defined uh, homomorphism from Z to any ring. So we'll look at other domains, but we'll look at a more general example. Let R be any ring. Then R of X is the polynomial ring with coefficients from R. Fix an element A in R. So you pick one element. For each element, you will get a different homomorphism. Define phi of A from R of X to R by phi A of f of X is equal to f of A. This is a ring homomorphism. Yes. We are take pick a constant. We are picking a constant because for each value of a, this is different. You pick you pick one value a in the ring R. For example, consider R to be z. Then from z of x to z, you have, let's say, phi 2. Then phi 2 of x square plus 1 will be 2 square plus 1. You substitute you substitute the value. That's all. Phi 2 of x plus 2 is 2 plus 2. So this is called the substitution homomorphism. You take one value in R and substitute that into every polynomial in R of x. And the image of a polynomial is simply the value you get when you substitute the element of R in place of x. That element. Then what will happen if what is phi 2 of a constant? What is phi 2 of 3? The x plus 2 got mapped to what? 2 plus 2. What if there is no x? What will you get? You will get 2. That's all. Yeah. So constant will get mapped to itself. So every element of R is covered by this homomorphism because phi 2 of a constant is a constant itself. So every element in R is an image of some element in R of x. Okay, but we have to prove that it is a homomorphism. We haven't shown that yet. Can you prove it? First, we have to show what? Closure under operation, preservation under addition. So we have to pick two elements from R of x. But yeah, you can say f of x and g of x because they are both polynomials in x. Yeah, yeah, yes. This is simply substitute. Yeah, this is simply be f of a because substitution. That's how it works. For polynomial addition, f of x plus g of x. Um, and if we call that h of x, then h of a is simply f of a plus g of a. But f of a and g of a are what? Simply phi of f of x, right? So operation is preserved under addition. Similarly for multiplication. This is simply f of a into g of a. Just by definition of this. So we define the product of two functions by as the pointwise product. So if h of x is the function f of x times g of x, then h of a is defined to be f of a dot g of a for all a in the domain R. So that's simply the by definition of the product of two polynomials. But then f of a is phi a of f of x and g of a is phi a of g of x. And finally we have phi a of 1 should be equal to 1. But right now we saw, right? Constant simply goes to the constant itself. There's nothing to substitute. So this is simply 1. Therefore, this PA is a homomorphism from the polynomial ring with coefficients from R to the ring of coefficients R. Is that okay? Okay. So once we saw this, once we saw subgroups, we also saw the kernel and the image. So here the image is not important for us, but kernel is important. So before that, I claim that let phi from R to R dash, be a ring homomorphism. Then phi from R plus to R dash plus. You consider only the plus operation. Then it is a group homomorphism. This is straightforward, right? Because what does it mean for it to be a group homomorphism? It means phi of A plus B must be equal to phi of A plus Phi of B. But that is one of the conditions for it to be a ring homomorphism. So every ring homo and when in a ring with respect to addition operation, it is an abelian group. So you can also look at it as a function from the group R to the group R prime. And when you look at it that way, it will be a group homomorphism. So for group homomorphism, we had a kernel, right? The kernel for the ring is the same. Yes, yes, that's all. That's the kernel. Uh, Kernel in linear algebra, it is called null space. Null space of the matrix. It's the set of all vectors such that when you multiply by the matrix, they go to the zero vector, right? Uh, so there also sometimes it is called the kernel of the matrix. the null space. So here, in abstract algebra, you call it the kernel. But here, yeah, that's all. There you call it null space. Here you call it kernel. There's a matrix. Here you have, instead of the matrix form, you have it as a function. So the kernel, see, now when you define the kernel for the ring homomorphism, we will not look at the additional properties of the multiplication that we have. We will simply call the kernel of the group homomorphism. So every ring homomorphism is a group homomorphism, right? And for the group homomorphism, you have a kernel. So all the elements that go to the identity under addition, the identity is zero, zero in R prime. So all the elements that go to zero in R prime under phi, that is simply the kernel of the ring homomorphism also. So given a ring homomorphism phi from R to R prime, the kernel of phi is defined as set of all elements in the domain such that their image is the zero element, the additive identity. This is obviously a subset of R, right? Because all elements might, these are elements of R, so it might be R itself or it might be a proper subset also. Anyway, it is a subset of R. And I don't know if I showed it, but uh, the kernel is an additive. I think I showed it. The kernel is an additive subgroup of R plus. There, when you had a group, the kernel was a subgroup of R. It here also it's the same. Is it a subring according to our definition of subring? Is a kernel a subring of R? Yeah. Huh. We must show that it is associative, commutative, and has the identity. Ah. Is it? Does one belong to kernel P? Is it even possible? Yes, yes. Yeah. So unless the ring is simply the trivial ring where 0 and 1 are the same, as long as 0 and 1 are different, then we must have phi of 0 is 0 and phi of 1 is 1. So phi of 1 cannot be 0. That means 1 cannot belong to kernel. Kernel is a set of elements that are mapped to 0, right? Yes. So 1 is not in the kernel. So kernel cannot be a subring. So that is kind of a problem because now what you are left with is simply um, the point of the multiplication kind of went away now, right? It's only a additive subgroup of R plus. Then how is this kernel any useful? Uh, So it is useful in this way. If it is the kernel of the subring, kernel of the rings kernel of the ring homomorphism is useful because it has the following properties. First, let me write down. It is not the useful property is this. Suppose A belongs to the kernel. Some element is in the kernel. Kernel is a subset of R, right? The domain. These are elements from the domain that are mapped to 0 in the codomain. So it is a subset of the domain. Let R be any element in the ring. So this could be an element that is not in the kernel also. And you take the product of these two, Ra. What is P of Ra? Here. So it is 0. But we saw that I told you the property that I showed, I think, last class. Any element into 0 will give you 0. So this is 0. So what does that mean for Ra? P of Ra is 0. Because A and R both are elements of the ring. So by closure, Ra will be in the ring. That is directly from the ring. Or A is in the kernel, R is some element in the ring, not necessarily in the kernel. When I took their product, I got that that their image is 0. What does that mean for Ra? Image of Ra is 0. What is the definition of the kernel? Yes, so regardless of what R is, Ra is in the kernel. So this has this interesting property that if A is in the kernel, for any ring element, Ra is in the kernel. Since we are looking at commutative rings, AR is also in the kernel. Actually, if you are not looking at commutative rings, then this would matter actually. Whether RA is in the kernel or AR is in the kernel, would have to differentiate between that. Since you are looking at commutative rings, it's fine, both are same. If A is in the kernel, RA is in the kernel. That is the nice property of kernels that comes from the multiplication, right? So it's something different from the kernel under the. Of course, the way you get it is simply the kernel of the homomorphism considered as a group homomorphism. But it turns out that it has this additional property under the product also. So this property is is what defines an ideal. When ideal I of a ring R is a subset of R satisfying two properties. First property is Yes, I is an additive subgroup of R plus. That's I plus. I can write I plus is a subgroup of R plus. Second property is if A is in I and R is any ring element, then RA is in I. So a kernel A is an ideal. That is one example for an ideal. So is that clear what an ideal is? Yes. Okay, let's look at kernels of the examples that we saw earlier. We had P from Z to 4Z, where P of K was K bar. What is the kernel here? What are the elements that go to 0 bar? Yeah, so kernel P is 4Z. This was supposed to be Z mod 4Z. Or you can write 4M, M in Z. All multiples of 4 go to the equivalence class 0. Because mod 4, they are all 0. Similarly, if instead of Z mod 4Z, you had P from Z to Z mod NZ, again you would still have P of K is equal to K bar. Kernel would simply be NZ. All multiples of N go to 0 bar. What about the other example? Phi 2. What is the kernel? So it's a set of all f of x in Z of x such that phi 2 of f of x is the 0 of z, which is simply 0. But what is phi 2 of f of x? Simply substitution map, right? F of 2. So f of 2 is 0 means 2 is a root of the polynomial. Yeah. So phi k is from z of x to z, where k is an integer, and kernel of phi k, set of all f of x in z of x, such that f of k is 0. So k is all the polynomials with root 2 are in the kernel of phi 2. One more thing you could say is I showed in one of the classes that if if x minus alpha divides f of x, then f of alpha is equal to the remainder, right? Or something like what was it? Um, Sorry, that was not it. What was it? The remainder you get when you divide f of x by x minus alpha is f of alpha, right? Do you remember? Which result was that? We didn't do it yesterday. Here we had so if you divide g of x by x minus alpha, you can use the division algorithm to write g of x is equal to x minus alpha into q of x, the quotient, plus r of x, the remainder, where r of x is either 0 or the degree of r of x is less than degree of x minus alpha. But degree of x minus alpha is 1. So degree of r of x is less than 1 means it is a constant polynomial, right? Then we substituted alpha on both sides. We got g of alpha is equal to alpha minus alpha times q of alpha plus r of alpha. But r of alpha is a constant, right? Um, so regardless of what values you substitute, r of x is the same. So for all values of x, r of x is equal to r of alpha. Now r of alpha is equal to g of alpha. So r of x is actually simply the constant value g of alpha. So when you divide g of x, any polynomial g of x in r of x by x minus alpha, the remainder you get is g of alpha. Now, in today's lecture, if you divide x minus k, f of x by x minus k, what is the remainder? F of k, right? If you divide g of x by x minus alpha, remainder is g of alpha. Instead of g, we have f here. So if you divide f of x by x minus k, the remainder is f of k. But we are saying f of k is 0. What does that mean? The remainder you get when you divide f of x by x minus k is 0. Yes. So it's all polynomials that are divisible by x minus k. Or you can simply say it's all multiples of x minus k. And but here the multiple in the sense that it is x minus k into h of x for any polynomial h of x. Those are all the multiples of x minus k. H of x can be a constant or it can be another polynomial. And these are all divisible by x minus k. Okay. Okay, we'll stop here. We have some properties of ideals left. After that, if you want, I can do problems. If you don't want problems, you can skip to. Uh, you want problems or no? Okay, we'll do problems. And then after that, the remaining topics in rings and ideals will get progressively harder. Um, I can do them later after the course is over, but within course time, these topics are harder to cover. So we can move on to fields, cover the basics of fields after some problems. So tomorrow I'll do problem. Day after tomorrow also I might do problems. After that we'll start with fields. Yeah, once we are done with it, we'll go back to groups and cover all the topics in groups. Then we'll come back to rings and cover the remaining things. Okay. Good night.